Hello and what's up, guys? Today is the first session of this series about Newton's viscosity law. This law says that if we have two adjacent layers of fluid in motion and one is moving with u, velocity of u, and the upper one is moving with velocity of u plus du, we consider it, and the distance between these two layers is dy, for example, and there is a tau shear stress imposed between these two layers. This tau is proportional to velocity gradient. What is velocity gradient over here? U plus du minus u over dy. This is our velocity gradient across these two layers, okay? And it gives us tau is proportional to these u's cancel each other and du over dy, okay? In mathematical form and in its exact form, we write it like this: tau equals to mu du over dy. Here tau is our shear stress, mu is dynamic viscosity, and this is velocity gradient across flow direction. What does it mean by across flow direction? In the figure, this is our flow direction, okay? Everybody knows this. Across flow direction means in this direction. This is across flow direction, okay? This is the important part of this, let's say, formulation, okay? Newton's viscosity law is just a law, and it's not a result of any other manipulation of other formulas or other equations, and we accept it as an obvious law of nature, okay? The simplest problem in this subject is Couette flow. Couette flow means, this is a Couette flow. Let me write it first. Couette flow. Couette flow means a fluid, this is a fluid, flowing between two parallel plates, these two parallel plates, and flow is here, okay? This is called Couette flow, okay? Our aim in this problem is to prove that for a Newtonian fluid flowing in Couette flow configuration, the velocity profile is in linear form, okay? Linear. What does it mean by linear? Here in fixed plate we have a velocity of 0, u is equal to 0 over here, and at the top plate we have velocity of u capital, u equals to u capital, okay? We are going to prove that for Newtonian fluid flowing in this configuration, the changes between u equals to 0 and u equals to capital U is linear, is in this form, okay? It changes linearly from 0 to u capital. For this purpose, first, let's consider an infinitesimal element inside flow field, okay? Assuming the shear stress imposed at the lower surface is tau, and the shear stress imposed at the upper surface is tau plus d tau, okay? So, and the area parallel to flow direction, this is flow direction, area to parallel to flow direction is dA at both top and bottom surfaces, okay? Now, writing Newton's second law of motion for element. So sum of forces in x direction, this is our x direction equals to mass of our element multiplied by A of element in x direction. But in x direction, the A is 0. Why? Since velocity does not change with respect to time, there is no acceleration in x direction. Okay? So, as a result, sum of forces in x direction equals to 0. Now writing forces one by one. The force imposed at the lower surface is minus tau dA. Why minus, guys? Do you know why minus? Because this is in negative x direction. Plus tau plus d tau at the upper surface multiplied by dA equals to 0. And the reason for this plus is that tau plus d tau is in positive x direction. Okay, now expanding this equation gives us minus tau dA plus tau dA plus d tau dA equals to 0. These two cancel each other, and finally we have d tau dA equals to 0. As you can guess, this dA is not equal to 0 because we considered an infinitesimal element which is not 0 in the figure. Okay, as a result, d tau have to be 0. Okay, putting d tau equal to 0 means a differential of a variable equals to 0. So that variable is no longer a variable and it's a constant. So tau equals to some constant. I call this constant as, for example, tau naught. You can name it as A naught, B naught, or whatever you want. I call it tau naught. So from Newton's viscosity law, we have tau naught equals to mu du over dy. This is Newton's viscosity law. From here, we have tau naught over mu dy equals du. This is a simple differential equation which results in u as a function of y equals to tau naught over mu multiplied by y plus c1. Okay, c1 is our integration constant. Also, there's a point here. This tau 0, tau naught over mu is also a constant. I call it c naught. But this tau naught is not determined yet. Okay, so our velocity profiles takes the form of u as a function of y equals to c naught multiplied by y plus c1. We have two unknown constants here. Unknown constants. Okay. For determining these two unknown constants, we need two boundary conditions. So we need two boundary conditions. What are those boundary conditions? The first one is at y equals to 0. What do we have in y equals to 0? In y equals to 0, we have velocity of 0. Okay? So we have u equals to 0. At y equals to h, what do we have? In y equals to h, at the top plate, we have u equals to capital U. So u equals to capital U. So from the first one, we have c1 equals to 0. From the second one, we have c naught equals to capital U over h. Finally, putting all together, we have u as a function of y equals to capital U over h multiplied by y. This is our final result for this problem. Also, there is a point we should consider in this question, in this problem, and it's that shear stress is constant everywhere across flow direction. What does it mean? It means that if you are at y equals to 0, shear stress is tau naught. If you are at y equals to, for example, h over 2, half the distance, tau equals to tau naught. If you are at even h at the top surface, at the top plate, tau equals to tau naught. If you are at y equals to whatever you want, tau equals to tau naught. The exact value for tau naught, exact value tau naught equals to mu derivative of u with respect to y. It's this coefficient is u over h. This is the exact value for tau naught. Please don't hesitate to ask any question, and you can find my contact information at the description.